Okay, we have our next speaker, Danfei. He's assistant professor at Georgia Tech. He has a lot of work on task and motion planning. His research focus is on robot with flexible high-level planning abilities and robust low-level sensor control. So let's welcome him.
Thank you very much. Mic check. Okay. All right. Awesome. So in case you checked the schedule before 11 p.m. last night, you saw a different title. I decided to change up the talk last minute because I thought this topic is more timely. It's timely, and also I think maybe stir up more discussion, hopefully. So, all right, let's start. So I'm going to start with sort of a story back in 2019. 2009. Computer vision community was grappling with scaling up image recognition, and a pivotal moment was ImageNet. It wasn't about just collecting more images. It was about what images to collect and how they were organized using the semantic hierarchy of WordNet synsets. Who have heard of synsets? Great. I'm not at computer vision conference or an LP conference. So it's basically a hierarchy of like semantics. For example, there's entity, physical thing, object, physical object. So it's a hierarchy of how do we organize visual concepts, right? Like bird, different species of birds, different types of like sports and these kind of things. This really has provided a structural backbone to systematically cover meaningful visual concepts. And this was one of the trillion-dollar questions, I think, that propelled the field of AI in the past 15 years or so. And fast forward today, for language models and VLMs, their data set have evolved into what I call internet.zip, vast, largely unstructured data from the web. It's no longer structured like ImageNets nor synsets, but it's deeply rooted in a way that the data should be systematically collected to achieve coverage. But for robotics, we don't have internet.zip. So what is our equivalent? We see a lot of efforts recently, like Robot Turk, Droid, RT1, OpenX embodiment, to collect diverse robot interaction data. And they're all trying, I would say, tackling the same analogous question, which is how should we systematically curate data for robot learning? And specifically, what should be the synset for robot data? And we can imagine the answer should be much, much more complicated than just like hierarchy of semantics, and anticipate to be one of the most important questions to be answered in the next 5 years, given how fast the field is progressing. Just to be conservative. I don't have a definitive answer today. I want to share some promising ideas from our labs is exploring. And to unpack this challenge a little bit, we're facing at least 3 major challenges to achieve coverage. First, like what I mentioned, there's no robotics internet to download. We need to generate data from scratch, either collecting in the real world or generating simulation. Second, the data space itself, with environments, goals, task horizons, behaviors, robot configurations, it's far less tractable than, say, image to object categories or image text, right? And there's a paradox, which is, I would say, the most important thing is to generate truly rich and diverse data. We often need an already competent agent to begin with, and this is essentially a chicken egg problem, right? And it's really the sort of the crux of the talk. And this opportunity is significant. We get to define and control data composition, diversity, and coverage, whether from simulation in the real world or a combination of both. And the control really allows us to study this like data curation problem for robot learning from scratch. Still a daunting challenge, but at least as a community or as a sort of evolving field, we get to redefine the problem and see what's important. And at least this leads to the main idea I'm trying to talk today. Is a conceptual system I call it Neuro-Symbolic Data Engine. It's an autonomous system designed to manage data generation and systematically expand the coverage of robot learning data. And the key idea is to integrate symbolic knowledge or tasks, environments, affordance, causality with neural grounding derived from environment interaction. And it will involve lots of external structural knowledge like defining environment factors to vary, what are the possible tasks to solve, and task planning to create meaningful tasks and goals and steps, and also have unstructured components like behavior generators to produce actions, what would be the learn policy or script controller, or even humans, right? Human demonstrators to break the chicken egg problem. And finally, some reliable verifiers to assess the outcome so that we know which data is good or bad. And ideally, the engine should manage data generation fully automatically in simulation or guide human-in-the-loop data collection in the real world. And at this point, it should have guessed that this engine matches characteristics of somewhat of a TAMP system, right? So, and the work I'll be covering today are mainly really about how to use TAMP as data engine to manage the data creation process. I'll be talking about how to use it for better training RL agents. How do you manage human demonstrators to collect more data faster? How do I supersize the collected data so that you don't have to collect all the data yourself? And at the end of the talk, I'll be talking briefly about a sort of a study on if you can generate data from large-scale data from scratch, what lessons can we learn from this in simulation that can be applied to the real-world learning? And hopefully by the end of the talk, convince you why this problem is so important and worthy of attention if you are not already studying this problem. And TAMP plays a very, very important role in this. So our first idea is to use TAMP as an engine to manage the data generation process. And typically, I won't repeat what TAMP is. This is a TAMP workshop. So it takes a task goal, use planning algorithms, symbolic logic to create a task skeleton. And these high-level actions are then grounded by some motion generators, like shown here, like push and pull and insert. And the question we ask is, how do we populate this skill library in the first place, right? Especially for complex long-horizon tasks. And it's the chicken egg problem I've discussed earlier. To generate data for learning, learning these long-horizon tasks, we often will need skills that can already solve part of the task. If you don't have those initial skills, how do we even begin to plan how to solve these tasks and acquire the skills to solve these tasks, right? So I mean, that's where sort of the help of TAMP comes in, because TAMP really describes the world both at symbolic level and also the level, continuous level for motion planning or optimization-based control. And our idea is to conceptualize skills within the library as neuro-symbolic skills. Each skill combines symbolic operators, like shown here, with the underlying neural policy pi theta, which is what we need to learn. And the point is that the operator doesn't just name the skill, right? It provides a specification for the data we need to learn it. It will write down what exactly we need to do to learn this skill, like what kind of data to achieve. And it basically, the operator defines the initial condition, the outcomes, like what it achieved, and what are the conditions for success, right? That can be used as verifiers or reward function for reinforcement learning. And really, so through these symbolic operators, TAMP isn't just planning to solve this task, it's planning the data requirement, like what data to generate to learning skills. And the forms the basis for using TAMP really as automated learning curriculum. Basically, in our work, we plan first necessary skills to solve a task. If a skill is missing or weak, if this is a data gap, then it decides which skills need to new data. The key idea here really is to use the combinations of already competent skills to learn a skill, to learn these, to reach the initial condition for these skills to learn, or what we call plan to learn. And if the prerequisite skills are not competent, then they train these skills, the prerequisite skills instead. And then the robot learner uses to generate data for training with RL or other algorithms. And the repeat is like what I call virtuous cycle. As data is generated and skills are learned, TAMP systems are expanded and enabling to solve more complex tasks and identify states where it needs to generate more data. Right. So just really quickly to show some results. Here is a kind of a typical like I would say for RL long horizon task, which is how do you put these two hammers in two doors? And you can notice that the configuration of these doors is that you have to close one before open the other. So you kind of have to learn the sequencing and also the underlying skills to this. And you see that during the learning process, we see in the beginning, you're like this is the only part of the learning process. You see it start to learn the opening skill, the blue bars. Then you start to learn more pick and place once you kind of master the open skills, and eventually more closed skills get learned so that the next stage of tasking, right? So that's really the general idea here. And you see that it works better than other hierarchical systems, but that's kind of by leveraging the priors of TAMP systems. And you can sort of run this on real robot. It's a bit clunky, but makes a direct sim to a real transfer. I won't finish the video here. We're not only limited to reinforcement learning because, like these days, a lot of people, the robot learning community kind of have converged on this idea. We should just use more real-world data generated by human. And the same ideas can be used to manage the human data collection process, where the humans are considered as skills, right? So we basically provide skill demonstrations for the part of the tasks that are hard to solve according to the existing skill library. So the idea here is to use TAMP as an interactive demo collection system, where we use TAMP again to generate task plan. And the human developer is asked to take over the control when a subtask cannot be solved by learned skill. And we train visual motor policies from partial developer demonstrations and the skill. The TAMP system, again, has a virtual cycle that as it gets more competent, less intervention is asked, and more complex tasks can be solved altogether. And one of the key design we made is TAMP-gated human in-the-loop operation. So basically, it asks that actively last for demonstration when it's needed. So we'll basically use TAMP to check success condition when it's satisfied certain effect conditions of the already competent skill. The human will take over through teleoperation. Data gets collected for these kind of more complex type of open and led of like these Keurig K-cup machine. So real quick results, you can see that on right hand side will show when it's using TAMP or when it's doing the teleoperation. So you can see there's this sort of back and forth. And the cool thing is that a human can actually simultaneously manage a fleet of a robot because it's sort of an asynchronous process. So we show that we can teleoperate like at the same time 5 robots at the same time to produce data scale. And we also show in the real world that we can kind of solve complex tasks with a lot fewer demonstrations because the skills are learned for only selected part of this. The rest of it, we kind of replace that with optimization-based controller or just motion planning. And in simulation, we really stress test this to collect a lot of demonstrations with human, and we show that within just 5 hours, we can collect 2,000 demonstrations for all of these diverse tasks, which is, I think, unheard of because it means those tasks are actually very, very difficult to demonstrate. So you can see the real value of like an easy evolving system that requires less intervention from you. And the third idea is that we don't want to just collect more data, right? We would or from human, we want to be able to expand the data set on its own by leveraging some learned representation or grounding. The idea here is that we want to basically transform some demonstrations collected for certain task configurations for certain objects to a different new object configuration or new object shapes without any learning. It's just optimization based. Like you can think of a trajectory optimization in some learned space. And what we can do here is to basically have one source demonstration and generate many demonstrations for slightly different object shapes and different object configurations so that I can use that to supersize your human data set. And we can also do similarly use a TAMP system to do long horizon stitching so that you only have to collect a little bit of skill level data on certain object, and you can supersize that for a lot of human data for a lot of different tasks and a lot of different objects. So overall, we're able to just collect 2 pick and place and then generate the data for all of these different configurations. And also can run this just as a sort of a planner on a real world because it relies basically on raw point cloud. So we can show that this can be used to train a lot of different policies, or sorry, solve a lot of different tasks with just 1 or 2 or a handful of demonstrations, essentially as a way to sort of optimizing collected recorded demos through learn representations based on point cloud. And we can also solve these classic TAMP problems like who use to kind of get things that are hard to reach and stack them on buttons. Right. Okay, so quickly, I want to talk a little bit about sort of the global picture here. We've shown really TAMP should be managed systems for data collection, whether you are an RL learner or a human data collector. And then the point is not really make it sound dystopian, but more like we want to achieve, again, the goal is to achieve systematic coverage of behavior so that we can achieve something like image, right? This is our sort of North Star. So with the tool I've developed, we have decided to kind of generate a large-scale data set and construct a systematic study to answer the question of really like what matters, right? What exactly does it matter in the generated data, and does coverage kind of improve the performance overall? So this is sort of our latest iClear paper on like what matters on learning from large-scale data set for robot manipulation. And what we did really is a sort of easy to use software called Mim Labs that lets you build your own system. So it's something similar to what we talked about before. We have this kind of similar to PBL. We define both these environment and task behavior domain. That I forgot the full name, but it was first developed by the behavior team at Stanford. So basically, you can write down these scripts to define all the environment factors, how you want these objects to be initialized, how you want your what skills do basically what are meaningful tasks, and basically specification of what data you want to collect. And we can also define these continuous factors to systematically generate these environments. And one cool thing is that we kind of fully automated data collection process where the data engine will ask you for them, right? It will basically say, here's what you need to do. Give me a demonstration for that. And when this condition is satisfied, it often prompts you for the next task or subtask you want to demonstrate for. And overall, you can just and then once the data is collected, a handful of demonstration for these subtasks will basically supersize it with the similar system as I've described before. And overall, we were to manage with just 2 or 3 students were able to generate 1 million task trajectories that are all meaningful demonstrations for a variety of environments and tasks and objects. So answer the question from 2 practical perspectives. One is what we call collector's perspective, where we want to see what data should I collect next to improve data set utility. And the second is that if you start with a large repository of data, like Droid data sets, if you've heard of it, how should I best use this data set? Because now we have a synthetic data set that's as large, right? So I won't get too much details into the collector's perspective because it's actually very interesting insights, but I will skip that. But the more actionable in the real world insight is the retriever perspective, where we want to see how best retrieve from a large source data set to improve performance for a target task distribution, right? Like you have an environment, you have a bunch of small amount of demonstrations. How should I retrieve the large scale data set so that I can improve this task performance within my small data distribution? We studied factors like camera pose, object texture, category, spatial arrangement, task objective, and we found that basically there are certain coverage patterns matter helps more than the other if you don't want just to retrieve all the data. And we actually see that retrieving all the data hurts, and you want to properly align with certain factors. And specifically, camera poses actually matter the most, right? If you have different camera poses, source template poses actually hurt to policy performance, even if the tasks are the same. And for object textures, it doesn't really matter. You can just throw in a new object. The policy will be able to learn a joint replication together. And spatial arrangement of object matters decent amount. So we showed this for a real Droid study where we download all the Droid data, and we extract metadata for these Droid data set, and we basically retrieve based on our simulation-based study. And we show that if you retrieve all of the data, it actually hurts the performance if you train it with in-domain data. And if you retrieve it, align the different aspect of it, for example, object poses or object categories, it improves the performance to various different levels. And there's some quantitative studies. I won't go into details, but check the code base and stuff out. We're still cleaning up code, which will be out in about a week or so. But yeah, definitely we'll make a release out of this work. Some closing thoughts. As a sort of the journey for robotics, equivalent ImageNet is like a foundational structural backbone for querying data set is still just the beginning. And for robotics, we don't have the internet download from, so there's the chicken egg problem. Really, is a coupled problem of learning and data generation. And we really need an automated system to cover data for us. We cannot possibly do this just by heuristic or just, I decided to collect this data for this environment, for this on this day, for this task, right? That is not going to be scalable. And the system needs to have rich semantic priors, for example, from LLMs, VLMs, and robust groundings of meaningful variations to the environment, tasks, and behaviors, which is what I think TAMP-like system can offer. And answer to how to systematic cure data for robot learning, I think in my view, may ultimately be as difficult as how to build a general purpose robot, because these problems are fundamentally coupled. And with that, I would like to thank my lab and my sponsors, and thank you.
Since we started late, we probably have time for 1 or 2 questions. Okay, I have a more general question.
Sure.
So you've been collecting data and train the policies. Do you think going forward that we will have a more general way to collect data? For example, if you think of all the small tasks that we perform daily, do we need a demonstration for all of them, or is it more general way?
That's a good question. I think that's a scientific question in the study, but in order to answer that question,
that's true.
So another level.
Yep. Thank you. Thank you.